I've rewritten the integral here to keep us moving along. EP, it's the integral minus L over 2 to L over 2. I went ahead and separated the I hat and the j hat. So this was the cosine component. This was the sine component. So now we have to do this big, nasty integral. All right, well, let's just do it. So EP here on the I hat is, what's it going to be? Well, it's minus KE lambda. You can always just write down the constants, not a problem. And we're integrating a squared plus x squared to the minus 3/2. So if we would just want to do that the normal way, that would just become minus 1/2. So you would divide by minus 1/2, which is like multiplying by minus 2. And you'd write a squared plus x squared to the 1/2. Because it's minus 3/2 goes to minus 1/2, it's in the denominator, so it's 1/2 in the denominator. But then you also have to divide by the derivative of this thing with respect to x, so that's 2x. So it's lucky that that x is there to get canceled out. So we divide x by 2x, and we get a half. So that's the integral of that thing, and then we evaluate it from L over 2, or from minus L over 2 to L over 2. And that's your I hat component. Okay. So we'll do the evaluation in a minute, and we don't want to get all of our fun here at once. Now, this other integral, you can't do as straightforward. You can't just bring that up to the minus 1/2 and divide, because you divide by minus 2x, and there's no x there to cancel it out. So for this, we're going to use a table. Meaning I looked up this integral in a table. So what we're going to use is that if you have the integral of, in this case, dx over a squared plus x squared to the 3/2 in the bottom, if you're in this case, that's equal to, we put an x in the top over a squared, yes, x over a squared times a squared plus x squared to the 1/2 in the bottom. You may not believe it. If you don't believe it, take the derivative of this. It'll turn into that. Okay, you can go the other way. So that is actually true. I got that from a table. So if we apply that to this, then let's see what we get. Well, we have our k e lambda along for the ride. And this says we need to put an x up here. That's fine. And it says, but actually we had an a along for the ride as well. So let's go ahead and put that a there. Okay? Because you notice the a wasn't in here. It's just another constant that we have moving along. And then it says that in the bottom we have a squared, and x squared plus a squared, or a squared plus x squared, same thing, to the 1/2 in the bottom. Okay. So there we used that standard integral there. So that's also from minus L over 2 to L over 2. Okay? So now let's apply our limits and see what happens. That's j hat. So now we're going to apply the limits minus L over 2 to L over 2 and see what we get. So let's see, a lot of stuff's going to go away here. That and that go away. The 1/2 and the 2 basically cancel to make 1. So pretty much what we have here is ke lambda. I'll pull them out. And we're going to plug in L over 2 into the x. And we're going to plug in minus L over 2 into the x. So this is going to be 1 over a squared plus, that's L squared over 4 to the 1/2, all right, minus, and then plug in minus L over 2. Okay, the ke lambda's out here, 1 over a squared plus minus L over 2 squared is again just L squared over 4 to the minus 1/2 to the 1/2 on the bottom, like that, I hat. Okay. Well, look at this. We have a term minus itself. It's 0. The whole thing made 0. So again, eventually we're going to make it over here, and that's 0 on the I hat. That tells us that the field has no x component. Okay? That one came out to be 0. Let's see. Hopefully this one won't be 0, because then we have no field. That can't be right. So let's write ke lambda. Let's pull out the constants. Ke lambda. And actually you'll notice that this cancels one of those. So everything's going to be over a. I'll go ahead and leave it on the inside, though, just because I'm that kind of guy. And now we're going to plug in L over 2 into x. So it's going to be L over 2 over a times the square root of a squared plus L squared over 4 to the 1/2 minus And then we're going to plug in minus L over 2. So minus L over 2. And then the bottom is going to be A squared plus L squared over 4 to the 1/2, like that, J hat. Whew. Just enough room, okay? So this whole thing, when we put it together, equals what? This was 0, 0 component on the I hat. And the J hat, it's not going to make 0 because this minus makes a plus. It's L over 2 minus L over 2. It's really L over 2 plus L over 2. It's L. The fact that we had an x here kept this one from being 0 because when you plug in L over 2's in an x squared, it's the same thing. So minus itself is 0. But when you plug them in with an x there, it's not the same thing. And that's what made it not be 0. So then we get plus KE lambda. This becomes L over what's left? A times the square root of A squared plus L squared over 4 J hat. So the answer is it does have a value in the J hat direction, in the Y direction. There is a field. So this then is the answer. 0 in the X hat and that expression in the J hat. Okay? You could also notice that some books you might see it written as Q. They might set this whole problem up as a rod with a uniform charge, big Q. You could convert it to your own charge density, or you could see what is lambda times the length. That's the total charge on the rod. So if you have this in your textbook you're using and you see a big Q there, that's the reason. So you can think of it as a rod with total charge Q, or you can think of it as a rod with charge density lambda and length L. You can also look at this and realize it does make sense. It looks like Coulomb's law. It's K, Q, and this should have a unit of a length squared, and it does. Here's a length, and here is a length squared, square root, here's another length. So everything makes sense. Okay? It's a good way to check your answers that way. It's a good idea. So, question, let's see. The question this time is what? Prof SP, what methods can we use to solve the integrals? Okay, right. So for the y-axis integral, I went to a table because it's not an integral I can just do manually. So I looked it up in a table. And the answer is you can use any method you want. Okay? This is not a calculus class. We're not making you memorize a bunch of definite integrals. So you can look them up on tables. You can look them up on your computer. You can do it on your phone. You can use Mathematica, whatever you want to do. For the exams, when we limit what materials you can use, we'll make a table of integrals available with all the integrals that you might need for the exam. So don't worry about memorizing definite integrals, at least for this class.